So far, I talked about growing these nanowires using the vapor liquid solid technique on a substrate. Typically, the substrate could be silicon or sapphire, depending on what you want to do for application and what type of nanowire that you want to grow. On the other hand, there may be applications which require bulk samples. Those bulk production of nanowires could be done using a microwave plasma reactor. So this particular reactor I'm showing here has been used for growing oxide nanowires. So the microwave frequency is 2.45 gigahertz. It's a quartz tube reactor, approximately 4 to 6 centimeter diameter, and the plasma zone itself in the center of the reactor is about 30 to 40 centimeter, and the inert gas that you can use here is either argon or nitrogen, and that gets mixed with oxygen, and the power that you use is approximately from 0.3 to 3 kilowatts. You don't need catalyst, and you essentially, if you are interested in growing, let's say, zinc oxide, then you use zinc oxide as a powder source. You drop it in the at the top, and oxygen is also provided along with the carrier gas, which is argon or nitrogen. So 20 to 200 nanometer diameter and several micron long nanowires have been grown by using this method. So the length of the nanowire depends on the length of the growth zone. So if you shorten the zone, the nanowire length will be smaller, but if you make it longer, then the nanowires will be longer. This image shows samples of tin oxide in a bulk produced using the microwave reactor. So these are highly branched, mat-like networks. So the feedstock here was 1 to 5 micron tin particles with 12 liters per minute of air and 2 liters per minute of argon and 50 cubic centimeters per second of oxygen, and using 1.5 kilowatt of microwave power. Now I want to talk about some of the properties of nanowires. Earlier on, as a motivation, I mentioned that the nanowire diameter, when it gets smaller, the band gap increases. This has been proved for a number of materials. I'm showing here for silicon. The silicon nanowires were grown using vapor liquid solid technique by this group in Hong Kong, and then they used scanning tunneling spectroscopy to measure the band gap. They were very careful in removing the native oxide surrounding the silicon nanowire, so that way you could get a reliable measurement. So when nanowire diameter is about 7 nanometer, the band gap is very close to the bulk value of 1.1 eV for silicon. Then when the nanowire diameter gets smaller than 7 nanometer, the band gap increases gradually. Eventually, for something like 1.3 nanometer silicon, the band gap reaches something like 3.5 eV. So that's really wide band gap. In fact, almost reaching the value of diamond. So this is a very clear demonstration of quantum confinement effect. The next property that I want to talk about is thermal conductivity of nanowires. People have experimentally measured the thermal conductivity of semiconducting nanowires, and there have also been many theoretical predictions. In both cases, the thermal conductivity as a function of temperature and the wire diameter have been measured. So when the nanowire diameter decreases, the thermal conductivity decreases. Also, when you increase the temperature, the thermal conductivity increases at low temperature, and then eventually at certain temperature, the thermal conductivity begins to saturate. An application summary for nanowires. I mentioned earlier on, pretty much all the elements on the periodic table and even variety of compounds have now been grown in the form of nanowires. So essentially, in all those cases, whatever the original applications that people used for thin films of the same material, nanowires could be used in the same set of applications, but with hopefully improved performance or perhaps cheaper. In that sense, silicon nanowires, they have applications in electronics and sensors. germanium nanowires, electronics and IR detectors, tin oxide nanowires. Tin oxide has been a major material for gas sensing. It has been used in the last 40 years in the so-called chemical field effect transistors. Now people have started using tin oxide in the form of nanowires in chemical sensors because of the higher surface to volume ratio of the nanowires provides better sensor performance. Likewise, indium oxide nanowires are being used in chemical sensors and biosensors. Copper oxide has been used in field emission device. Boron nitride nanowires are used as insulator. Indium phosphide nanowires are useful in optoelectronics. So these are all some examples of applications for nanowires. In the rest of the presentation, I would like to focus on some applications. The first application that I want to talk about is nanoelectronics. So the real question is, what is expected from alternative technologies beyond the conventional silicon CMOS? So the first thing is whatever a technology that you want to push, whether it is carbon nanotube based devices or graphene electronics or using nanowires of silicon or germanium, regardless of what the material is and regardless of what the approach is, it must be easier and cheaper to manufacture compared to CMOS. You need to have very high current drive. That is, you got to be able to drive a capacitance of interconnects of any length, very high level of integration, greater than 10 to the power 10 or 10 billion transistors per circuit, high reproducibility, better than 95%, reliability, the operating time hopefully about 10 years or greater, because we are used to that. Very low cost, you would be surprised. It's the current cost picture is about a microcent per transistor. Better heat dissipation characteristics and cooling solutions. One of the major problems we are facing with silicon CMOS scaling, as we get smaller and smaller devices with higher and higher current drive, the heat dissipation has become a serious problem. Also, we have been using this the same architecture in the last 4 or 5 decades, using the zeros and the ones. But what about novel architectures? They could be fault tolerant architectures or completely evolvable architectures based on our own brain neural type architectures. So these are all some of the areas the research community has been looking at. And also, all the devices we have used so far, the device technology, it's all based on the electronic charge. But how about using other state variables? For example, the spin of the electron, it is called spintronics. And so these are all the expectations from alternative technologies. So in that sense, compared to silicon and graphene, using nanowires as a nanochip component has some advantages because you can still use the familiar elements like silicon and germanium in the form of one-dimensional nanowires, and they are not exotic like carbon nanotube or graphene. And it's also possible to think of self-assembly schemes to create patterns. So without the standard lithography, it's possible to assemble fine nano features, and single-step growth process as a cost-effective method. There are a variety of unique physics possibilities. That includes a reduced phonon scattering, which is useful for logic. The surface sensitivity to external excitation, which is very useful for memory. And the quantum confinement I talked about would be ideal for both logic and memory. There are a variety of material choices. You can choose silicon and germanium, and then there are 3,5 compounds, there are 2,6 compounds, and whatever you need for interconnects, you can still do metals. So high level of integration also is possible. So it is somewhat easier to integrate these nanowires because of the familiarity with the materials. Of course, you need to develop new processing schemes because the structure of the nanomaterial has gone from two-dimensional thin film to one-dimensional nanowire. So here I show an example of a vertical surround gate field effect transistor. As you all know, transistor historically been horizontal. You have the source on the left and the drain on the right, and then the gate in the middle. Even as far back as the very first semiconductor technology roadmap, the community talked about making vertical transistors. The reason for that was people were afraid that at some point in time that we are going to run out of steam, particularly when it comes to lithography. So that was going to stop the Moore's law revolution. And so for that reason, the idea of a vertical transistor was floated even 2-3 decades ago, because when you make the transistor vertical, then lithography is not going to be the showstopper, because the source drain critical feature length scale now that could be controlled by the growth time in your chemical vapor deposition process. But that idea actually never was successful, because 2-3 decades ago, when people attempted to make a vertical transistor, they still had to rely on making a thin film and then do a pattern, end up using plasma etching to create the vertical structure. The unfortunate part of the plasma etching is it leaves the surface, the etched surface, too poor to be of value. For example, vertical transistors were fabricated for the same source to drain distance. The horizontal transistors, the conventional horizontal transistors, performed much better compared to the vertical transistors, because the vertical transistors had all kinds of surface problems. So that's why this vertical transistors never took off. However, now in order to get the vertical structures, you no longer have to rely on plasma etching. You can grow these silicon nanowires using the vapor liquid solid technique that I talked about directly, and you get really wonderful the surface. So this way now you can have source at the bottom and the drain at the top, and then a surround gate. So this particular image shows the process flow that was used to fabricate vertical surround gate FETs. The next thing I want to talk about under electronics is memory devices using nanowires. The requirements for an ideal memory, the memory community has always dreamed of making devices which will combine the best of SRAM, which is a static random access memory. It is known for its high speed, and then the non-volatile nature of the flash memory and the density of the dynamic random access memory. Combine the best of all three and then get a so-called universal memory, which is low cost and also scalable endlessly to very high densities. So that has always been a dream, and so far there have been a few candidates to achieve this quote and unquote universal memory. One is the magnetic random access memory. The second one is ferroelectric random access memory, and the last one is called Wovonic unified memory, which is actually named after the inventor of this memory. His name was Ovshinsky, and he proposed this in 1968. But it's more commonly known as phase change random access memory, or PRAM. Phase change materials are the backbone for the PRAM, and the phase change materials, they date back to the 1960s. In fact, the most common application for phase change materials is the optical storage media, which is a CD and DVD that we know. The popular material that is in the CD and DVDs is the germanium antimonide telluride. But there are other phase change materials as well: germanium telluride, indium selenide, indium antimonide, gallium antimonide, and a few other ternary compounds as well. So these phase change materials have two phases. One is the amorphous phase, the other one is the crystalline phase. In the amorphous phase, it is characterized by the short range atomic order, very high resistivity, whereas the crystalline phase is characterized by long range atomic order and very low resistivity. And you can go back and forth between these two phases in a reversible manner by applying heat to the material. I mentioned that the phase change materials have been widely used in optical storage media. Even in the 1960s and 70s, people already realized the possibility of making memory devices as well, using the same phase change materials. The advantages of using the phase change material to make memory include, you can have binary or even multiple, states, for logic levels. It is essentially thermally induced phase change. So when it is amorphous, it could represent 0, and when it is crystalline, it could represent 1. And much faster read and write times, improved endurance, because the flash memory typically lasts a few 10,000s of cycle, maybe 50, 60,000 cycles, whereas people have shown that the phase change memory lasts actually millions of cycles. And finally, since the data is not stored in the form of a charge, it is actually stored in the form of material phase, amorphous versus crystalline. The memory device is not prone to soft errors or susceptible to various types of radiation. So if it is so wonderful and if it has got so many advantages, then the question is, how come we don't have PRAMs already available widely in the market? There have been issues. One is, I mentioned that actually you can apply heat and then reversibly change the phase of the material between amorphous and crystalline. But the programming current needed, this applying the heat, it's accomplished by Joule heating by applying a current. So the programming current needed to drive this phase change, has been very high, and so that was one major problem. Then there were other issues, the Joule heating induced power dissipation issue. Then when in memory, one of the biggest goals is to start driving the density high. When that happens, when you're manipulating one cell, you could accidentally activate the neighboring cell, and that is called inter-cell thermal interference, so which will lead to scaling difficulties and it will limit the scaling possibilities.